Welcome to the part 2 of our discussion regarding quality assessment and performance involvement. But this time, let us focus more on quality monitoring and assessment tools. The precise techniques and mechanisms of quality control are familiar to every technical professional in the laboratory. The objective of this topic is to present a short survey of the concepts and terminology frequently found on professional examinations at the supervisory level. These concepts provide a baseline for the discussion of quality management in the medical laboratory. The tools for the measurement of quality and performance in the laboratory can be reviewed in 5 groups. 1. Statistical techniques that establish performance limits for the analytical accuracy and precision of testing protocols. 2. Graphic and monitoring methods that aid in review, troubleshooting, and decision-making systems. 3. Interpretative strategy for evaluating statistical and monitoring methods. 4. External programs that provide resources for the independent assessment of the technical performance of the laboratory. And lastly, the methods that are intended to monitor the delivery of the overall services of the laboratory as part of the healthcare team. From the multitude of statistical calculations available to the analyst, 4 measurements constitute the base for most quality assessment efforts. These statistical tools are quite familiar to laboratorians and are particularly applicable to situations in which performance criteria can be quantified. These 4 measurements are the arithmetic average or the mean, the standard deviation from the mean, the coefficient of variance, and the most widely used statistical calculation of all, the percentage. As what I have been teaching you from the previous discussions that we have, remember that accuracy and precision is the very core characteristic of a medical technologist inside the laboratory. Let's try to differentiate accuracy and precision. When we say accuracy class, it refers to the closeness of a result to the actual value of an analyte when performing a test, more commonly called hitting the bull's eye. Precision, by contrast, is determined by how well a procedure reproduces the same values. Let's make use of this dartboard as an example. Accurate class in a sense that is the degree to which the result of your measurement, calculation, or specification conforms to the correct value or the standard. That means you hit the bull's eye. That's why it's there. When you say precise, it means that during the testing process, you were able to arrive at a calculation or a measurement that are close to one another. Not all accurate measurements are precise, and at the same time, not all precise measurements are accurate. How? Allow me to explain it further. This diagram shows us the difference between accuracy and precision. Let's say, for example, if we analyze a triglyceride standard with a known value, so it means, class, that when you are using a standard in the laboratory, it has a predetermined value, meaning if your machine is about to be calibrated by a certain standard, it has to arrive at a certain value closest to the predetermined value. Okay, let's go back to our example. If we analyze a triglyceride standard with a known value of 200 milligrams per deciliter 5 times and obtain values of 169, 167, 170, 168, and 169, we can say that our methodology is extremely precise. However, its accuracy is way off and the procedure needs to be recalibrated. As what I have said, you have to use your standard once again. Because, class, if we say that your triglyceride standard and your machine is within limits, Your values should arrive within 200, 199, 198, 197, 196. So it should just play around those numbers when we want to have an accurate and a precise result. Miss, how can I say that the methodology is accurate but it is not precise? Let's say, for example, you still run the same standard, the triglyceride standard, and it should arrive at 200 milligrams predetermined value. But one of your value plays at around 201, 202, and then you also have 170. We also have 189. So there are outliers. In that example, you can observe that the values are very far from each other, not even close, but 2 or 3 of the values are closer to the correct or true value, like the 201 and then the 199. So look those numbers. That's why it's called accurate but not precise. Miss, can you also give us an example of not accurate and not precise? For sure. When you say not accurate and not precise, class, no values reach the correct or true value. So none of those were able to target the correctness or the closeness to the true value. And at the same time, none of your values are close to one another. Let's say, for example, you got 123, 99, 201, and 300, and let's say 400. And then the true value of your triglyceride standard only lies at around 200 milligrams per deciliter. This just actually means that your machine needs to be recalibrated, or there's a need for troubleshooting and fixing, or probably the standard use or the control use is already out of limit. Here is also another diagram that you could practice so that you will know the difference between accuracy and precision. The first diagram is high accuracy and high precision because probably the results of your quality control is within the true or target value, and at the same time, all the data in your QC are close to one another. The exact opposite happens when there is low accuracy and at the same time low precision, because none of the values reach the target value and at the same time none of them have values close to one another. Low accuracy but high precision happens when the data are packed at one part of the QC, so either lower or higher, but none of them targeted or reach the true or correct value. High accuracy but low precision happens when each of these data are closer to the target value but not close to one another. So there are some intervals per data or value. Okay, so much for that. Let's proceed to data population. In statistics is the pool of individuals from which a statistical sample is drawn for a study. Thus, any selection of individuals grouped together by a common feature, so they have a common feature class, can be said to be called a population. Common features include, by the way, depending on the interest of the person doing the statistical study, it can be the same year level, the same course, the same location, what else? The same sex, the same age, whatever is your subject of interest, then that is where you get your population. Okay, so we're done identifying our population. This means that the next thing that we will be doing is to get our sample from this population. A sample for statistical purposes is a part of a population that is used to analyze the characteristics of that population. It is a particularly useful technique when evaluating a population with a large number of entities, which makes it impractical to include every member in the study. In general, the larger the sample selected, the more representative of the population. However, as a general rule, most statisticians hold that a sample size of at least 30 is satisfactory for most studies. To be truly representative and also to avoid bias, samples should be selected at random. So it must be in a random manner that ensures that each unit of the population has an equal chance of being included in our study. The letter capital N indicates the number of observations, like for example, individuals, measurements, or values that make up the sample used for calculating statistical indexes. Let's say, for example, the laboratory and the pharmacy may be interested in reviewing the causes for a seemingly high frequency of gentamicin trough levels that exceed acceptable level. When you say trough levels, class, it means that there is a low point or the lowest point of activity of a certain medicine. Because when we calculate dosages in the hospital class, especially for pharmaceutical students, they always check the peak and the trough levels of each medication. Okay, let's go back to our example. So the laboratory and the pharmacy would like to check the frequency of gentamicin trough levels. So when you go to the laboratory section, they may have done several hundred gentamicin trough levels during the period of interest, of which 100 exceeded acceptable dose levels. Instead of having an in-depth review of every assay or every test class, the study may need to investigate only the 30 cases out of the 100 to find the cause of the deviations. That gives us a sample value of only 30 out of the 100 population. Is that understood? Another term that we need to define is Gaussian distribution. It includes a bell-shaped curve or normal distribution, or sometimes called frequency polygon and Lev Jennings charts. So they are all associated with the Gaussian distribution. All of these terms describe the statistical phenomenon that the members of a population are usually evenly dispersed around the population mean. But take note, class, that there are exceptions, such as when extreme values are included in the calculations, causing the curve to appear skewed. This important concept is the foundation upon which the acceptance or rejection criteria of the Westgard Rules and the performance limits of Lev Jennings charts are derived. Following the rules of a Gaussian distribution, the individual values of a population fall within the following boundaries. 68.2% are within plus minus 1 standard deviation from the mean. Plus minus 2 SD from the mean are within 95.4%. And lastly, 99.7% are within plus minus 3 standard deviation from the mean. With an understanding of these criteria, medical technologists can make an informed 95% certainty factor using the plus minus 2 SD standard, which is the criteria for accept and reject decision about the probability of a particular test run being in or out of control. There are also other two concepts such as percentage and probability. So these are part of our everyday lives, but you may also want to note the following points about probability for purposes of review. Probability, or sometimes written as a capital P, is usually expressed in statistical notation as a decimal, like 0.0 to 1.0, according to the likelihood of an event occurring. The nearer to zero, class, the less likely it is to occur. The nearer to 1, the more likely the event is about to happen. Probability may also be expressed in the negative. For example, the likelihood of an acceptable control value falling outside the plus minus 3SD range is only 0.003. How is it calculated? Remember that plus minus 3SD has a percent of what? 99.7%, right? So you subtract 1, which is the probability number 1, minus 0.997, giving it 0.003. In a more common language, probability is often expressed as a percentage, like there is a 50% chance of rain for today. Or sometimes you say it as there is a 0.5 probability of rain for today. The next term that we need to define is the mean. This is simply the arithmetic average for all the data contained in a sample population, such as the values obtained by running a normal glucose control for 1 month, or your score so that you can calculate for your midterm grade, and other sets of data that you can make in order to get the average or the mean. So how do we compute this, class? The mean is obtained by computing the sum of all the values contained in the population and dividing it by the number of values included in the calculation. I have an example here on the screen. So you have a data of 2, 2, 3, 5, 5, 7, and 8. In order to get the mean or the average of these data, you just simply add all of this and get the sum. And then divide it by the number of values that you have. So how many values do you have there? 1, 2, 3, 4, 5, 6, 7. So you divide it by 7. And there you go. The answer to this is 4.57. This means that your mean is 4.57 using all of these numbers. The mean and the median, class, is not almost always the same. So don't be confused with the mean and the median. Both of this describe the midpoint of a population. However, the mean is a calculated value, whereas the median is obtained by aligning the population from the smallest to the largest unit and selecting the midpoint. So the point at which exactly 50% of the population falls on both sides. In our first example here, class, this is already arranged in ascending order, and when you count it from both sides, the median number is 6. But if ever there are also cases, class, where there are 2 median numbers, then you add both of it, get the sum, and then divide it by 2, and that is your median number. Aside from the mean and the median, we also have the mode. The mode is considered to be the most frequent number in a set of data. Special cases happens when all the numbers occur in the same amount of time, so you consider it as no mode. However, there can also be more than one mode if more than one number is the most frequent. Then we also have the range. This is the difference between the highest and lowest number in the set of data that you have. So how do you find the range, class? You arrange them again from smallest to largest and simply subtracting the lowest value from the largest value. Next is the standard deviation. The SD, class, is a measurement of precision or the tendency of the values in each population to cluster, center, or scatter around the mean. A range of 2 standard deviations, plus minus 2, SD, is generally considered as the minimal limit for an individual control value to be acceptable because 95% of all legitimate values should be within this range. The mean and the standard deviation form the guidelines delineated in the Westgard Rules and the points plotted on a Lev Jennings chart. In calculating the SD for a particular control, the difference or variance of each value from the mean is used to establish the acceptable range for each control level. Calculating the coefficient of variance for each control level and procedure allows a comparison and check on the precision and variability of each method. The coefficient of variation is expressed as a percent and calculated by providing the standard deviation by the mean and multiplying the result by 100. So it is seen in your screen, the formula of CV. This means, class, that the smaller the CV value, the more precise the procedure. The interpretation of CV numbers must be placed in the context of the methodology of each procedure. Tests that closely follow Beer's law for endpoint reactions are expected to have very tight CV percentages, whereas the rate reactions used to measure enzyme activity usually experience a much larger range. Allow me to show you an example on how to calculate the mean, the coefficient of variance, and the standard deviation.
Find the standard deviation of the scores 6, 7, 8, 9, and 10. To compute the standard deviation, we need the mean and the variance. The mean is just the average of the scores, while the variance is just the average of the squares of the deviation from the mean. Okay, let's get started. Let's represent the scores with the variable x. The scores are 6, 7, 8, 9, and 10. You find the sum. This is 40. Then the average. 40 divided by the number of scores, which is 5. 40 divided by 5 is 8. So this actually is your average, or the mean. Let's represent the mean with the variable x bar. So the mean is 8. Next, we are going to get the difference of the score and the mean, or simply the deviation from the mean. 6 minus 8 is negative 2. 7 minus 8 is negative 1. 8 minus 8 is 0. 9 minus 8 is 1. 10 minus 8 is 2. Then you square the deviation from the mean. Negative 2 times negative 2 is 4. Negative 1 times negative 1 is 1. This is 0. 1 squared is 1. 2 squared is 4. Again, you find the sum. This is 4 plus 1, 5, 6, 10. Then find the average. 10 divided by 1, 2, 3, 4, 5 equals 2. Actually, this is your variance. And the square root of your variance is your standard deviation. So the square root of 2 is equal to 1.41.
To find the standard deviation, variance, mean, median, mode, and range for the given data. So the very first step is I want to make sure that the given data has been rearranged from lowest to highest order. That means in an ascending order. You can see that starts off with the lowest value and goes all the way to the highest, which is 28. So the very first thing we want to find out is median. Median is nothing more than just a middle number. Look at what is the median over here. Of course, obviously 15 is a median number because 3 values is on the left hand side and 3 values on the right hand side. So median is 15. So what is the mode, by the way? Mode is simply the number, the values that show up most number of times. Over here you can see 11 is showing up twice and 20 is showing up twice as well. So that means we have a 2 modes, which one are what? 11 and 20 are our modes. And they are showing up how many times? They are showing up twice. Finally, our range is simply what? Range is over here, which look at the lowest value is what? The smallest value is 7 and the highest value, the maximum value is what? 28. So range is simply what? The biggest number minus the smallest number. The biggest number is what? 28 and minus, you put always a minus, and the smallest number is what? 7, and you subtract simply, that turns out to be 21. That is our range. And finally median, mean, I'm talking about mean, which is represented by x bar. Mean is x bar. Over here you see this means that formula is what? Sum of the x values. That means all the data values divided by the total number of values. So we want to add these one up. So this is going to be x bar is going to be simply add all these value up. So 7 plus 11 plus 11 plus 15 plus 20 plus 20 plus 28, add them up, divided by, look at this thing, how many values are there? To data size, or the sample size is what? 7. So if you add the top part, which is what? 112 divided by 7 is going to give you what? 16. So 16 turns out to be our mean. So in this step, we will go ahead and fill out all our data values, which we call x values, in this table. As you can see, these one, the very first column on the left hand side, I put down all data values from 7 all the way to 28, and I'm going to call them x values. The next column, I put down all our mean values, which is, we call it x bar. We figured out these values in the previous step, as you can see, these one. So the next step, I want you to find x minus x bar, means x, the first column minus the second column. 7 minus 16 is what? Negative 9. Likewise, 11 minus 16 is going to be negative 5. 11 minus 16 is again negative 5, and that's going to turns out to be negative 1. This is 4, this is 4, this is what? 12. See how we got it? We just simply subtracted these two values. And the final column, the right hand side, what we're going to do is we're going to square the values that we just figured out. So negative 9 squared, negative 5 squared, all the way. So this negative 9 squared becomes 81. So negative 5 squared becomes 25, 25, 1, 16, 16, and 144. That's the very first step. We did this one. Now what we're going to do is we're going to add these numbers up on this last column. And this is, we will call summation, sigma notation of x minus x bar square. That means we are adding up all these sigma, means simply add them up. So once we add these things up, this turns out to be a what? 308. And now we want to find the variance. Variance is always represented by s square. So our variance is going to be simply s square. The formula is on the right hand side, as you can see. This is what? X minus x bar square divided by n minus 1. So we figured out this one right up here, which is 308 divided by n is how much? We know that these data values, these values are 7 of them. 7 minus 1 becomes 6, of course. 308 divided by 6 is going to give you 3 goes on and on and on. This is our variance. And now we're going to figure out the standard deviation. Standard deviation is always represented by s. So simply s is going to be simply what? The formula is this thing, the square root of sigma x minus x bar square divided by n minus 1. So we know that this on the top is 308 divided by 6. That is what? Square root of 51.333. If you take the square root of this one, that is going to be how much? 7.165 is our value. So thus our s turns out to be a 7.165. That is our answer. And finally, in this example over here, we've been asked to find the median. So what is going to be the median in this one over here? If you look at the median is going to be somewhere in the middle. Median means what? The middle number. We know that thing. So the middle number is going to be right in between. So right now over here, how we find when we have two numbers and we want to find the middle number, we just simply find the average of these two numbers. So median is simply what? Is you add these numbers up, 7 plus 13, and always divided by 2. That turns out to 20 over 2. So our median is going to be simply 10, and that's our answer.
Many other statistical tools are useful in studying both qualitative and quantitative problems. The preceding list covers only the basic techniques used in the laboratory. The next part of our discussion reviews some popular quality management methods that organize and present data in graphical and other monitoring formats to expedite analysis. One of the more difficult yet important tasks of any quality management program is turning the data collected from the monitoring process into information that can be used to troubleshoot and improve the production process. Data alone have no particular interpretative value. If placed within the context of other data points or material, however, they can become extremely useful in the decision-making process. This section outlines the most popular techniques in quality management for organizing, grouping, and sorting data into formats that assist the manager in evaluating the situation and in taking the necessary action to bring about improvement. With the advent of computer technology and desktop publishing, the boundaries for the graphical display of information have exploded. Bar and circle graphs are now being drawn in three-dimensional, multicolored topographical schematic figures that can incorporate and demonstrate the relationships between numerous factors on a single graph. The future of the graphical presentation of data is limited only by the imagination of the analyst. Let's first tackle the standard data plotting techniques, because this one class is the first task of any evaluation plan. So you have to arrange and present the data in a manner that facilitates further analysis. This procedure is referred to as the orderly array of data, meaning from lowest to highest value, chronologically by run or date, either in groups by sex and age, and all the other types of grouping that we can do. This step is usually part of the data collection plan, with continuous monitoring systems such as for a laboratory instrument. It is accomplished class by plotting the quality control data on a chart or graph as the test is being performed. Once the data have been arrayed in an orderly manner, the results can be presented in an informative format as a chart, a graph, or other pictorial display intended to demonstrate problems and potential solutions. Most of the methods here that I will be showing you are familiar already to you, both in the laboratory and from everyday life, because they frequently appear in news broadcasts, advertisements, classroom training material, and anywhere people may desire to make a certain point or pitch a product. Examples include a bar and pie charts and graphs, as well as the control charts used to plot the quality control data. Usually, class, those viewers of my videos or listeners of my discussions can relate to this, especially when plotting the quality control data in a chart. If you can remember from the part 1 of our discussion, some of the list of standard data plotting techniques are from Deming's 7 old methods. Remember that? So this has been around for a long period of time and has formed the basis of most quality assessment and management programs. Let's discuss the basic statistical graphs. The 3 most basic methods of presenting information when we were still in our elementary and high school are the circle or the pie chart, the bar, and the line graphs. These are used to illustrate the comparative size of different components or factors. Most other graphical display techniques are already modifications of these 3 methods. For sure, you're very familiar with this, the circle or pie charts. These are actually circular figures with areas marked off, either shaded or sketched, according to the percentage of each component compared to the entire whole. I showed here also in the diagram the correct way in showing your circle or your pie charts. It should not be inside, or the values should not be written inside the shaded portion. It should be placed outside with an arrow pointing to it. Okay? Next are bar graphs. This may be helpful in presenting comparative interpopulation and intrapopulation factors. This may range from showing the makeup of a population to comparing different populations with a key indicator or measurement. The bars on the graph may extend vertically, that means pabarog, varog, vertical, or horizontally, or higda horizontally, according to the preference of the preparer. The point is to present the information in a manner that best demonstrates and clarifies the information being detailed and that assists the users in their evaluation. And lastly, under basic statistical graphs are line graphs. These are particularly useful for plotting and tracking data over a period of time. So if you connect the dots on a Lev Jennings chart, for example, you have a line graph automatically. Line graphs class are very adaptable for displaying historical data. Control values, instrument parameters, workload volume, and blood bank refrigerator temperature monitoring are only a few of the many uses of the line graphs in the laboratory. When these values are plotted over a period of time, the patterns may be quite revealing about areas that need attention and require improvement, especially trends or deterioration in reagent or instrument performance. Another standard data plotting technique is the Gaussian distribution displays. There are two popular methods of displaying the frequency distribution characteristics of a population. Number one, that is a histogram. And number two, it's a frequency polygon. Both of this class illustrates the features of what again? Can you remember? A bell-shaped Gaussian distribution curve. A histogram uses a bar graph format to show the relative size or frequency of each class interval. A class interval is the statistical term for each part of the population. In the diagram that I have shown you, the difference between a bar graph and a histogram class is that the histogram doesn't contain any gaps, while the frequency polygons are the very familiar line graphs that give the frequency distribution its descriptive name, the bell curve. In both a histogram and a frequency polygon, a relative frequency scale represents the vertical axis of the graph. The values of the variable being studied are located on the horizontal axis. The values for each class interval are then plotted on the graph using the heights of the bars on the histogram to show the relative size and dots connected by a line for a frequency polygon. If the distribution of the population follows a normal pattern, the classic bell shape appears. Let's proceed to Deming's 7 old methods. Many other methods may be used to organize and summarize information in quality management studies. Each has its own distinct advantage and analytical purpose. Deming, however, has suggested 7 techniques with which the quality manager should be familiar, one of which is already the histogram, which we have already discussed, and the remaining 6, along with the storyboard technique, which has gained popularity in total quality management programs, will also be briefly described today. One of the 7 methods by Deming is the flowcharts. Quality management borrows the techniques and symbols of logic flowcharts used by management information system specialists to chart and analyze the specific process of information flow. They actually serve the same purpose in quality management programs by identifying and describing the exact sequence of work tasks and checking out ways for improvement by modeling alternative work routes. Usually, flowcharts are seen in government agencies where they show the step-by-step process of the entire thing that you're going to do, like getting a new ID or getting a birth certificate. Control charts are quite familiar to laboratorians, as one of the best examples of this technique is the Lev Jennings chart. By definition, class, control charts are used to plot control measurements against standards. Like, for example, upper and lower limits usually equal to the numerical value of plus minus 2 SD. Remember that plus minus 2 SD is the acceptable range in a quality control process. This is also used to identify whether a process is in or out of control. Next are Pareto charts. This is the term assigned to a bar chart that is designed to illustrate the classical Pareto principle. Remember the Pareto principle? It states that 80% of all problems can be attributed to 20% of the possible causes. According to this concept, if the problems are matched with their causes and plotted on a bar graph, the area in which managers should devote the majority of their attention and energy become readily apparent. To be honest, in the laboratory setup, I have never tried using a Pareto chart, though it has been taught to us in school, but I have never seen a Pareto chart in person. Another standard data plotting technique under the 7 old methods is the cause and effect diagram. Cause and effect diagrams class have several other names, including Ishikawa diagrams after Kaoru Ishikawa, who introduced this tool, and also called fishbone diagrams because of their appearance. This method, as the name implies, is used to identify the possible causes or contributing factors of problems or quality defects. The problem is placed at the head part of this fishbone diagram, with possible causes branching out of the backbone in the workflow direction. We also have run charts. A run chart is a line graph used to display data over a period of time. Run charts are also called trend charts, as they are designed to show patterns of performance. These may be used in the laboratory in a variety of ways. For example, tracking missed phlebotomies or redraws, data entry errors, or the number of tests that have to be rerun. The charts can be as general, like per shift, per section, or per department, or as specific, like an individual, instrument, AM or PM collection, as the study warrants. Scatter diagrams also belong from the 7 old methods. This method is used to show the relationship between one variable and another. A study may, for example, review the level of an antibiotic maintained in a patient compared to the time a sample was collected. So it's either the peak and trough studies. A graph is prepared with the concentration of the drug on the vertical axis and the time of collection after administration as the horizontal base. The results of each sample are plotted at the appropriate site on the graph and the pattern analyzed to check dosage and collection timing procedures. A big advantage of a scattergram class is that all data points, not just the summary statistical indexes, are plotted on this graph. That's why it looks like this. Usually, you can see scatter diagrams from a flow cytometry instrument in the laboratory, usually a hematology analyzer. And last but not the least are storyboards. Storyboards refer to the technique of using a pictorial sequence on a flip chart or other visual aid to tell the story of a quality management project. The presentation may be very elaborate, containing many of the previously discussed methods to illustrate how the investigators conducted the study, or may be a simple outline of each stage of the project. A very good but a simple example of a storyboard is the hand washing technique announcement in the restrooms that you can see, where there are photos of the step by step process on how to properly wash your hands, like what should be the placement of your fingers, the palm, how many seconds you should be washing it in that position. That one is a very good example of a storyboard. Aside from the basic statistical tools and Deming's 7 old methods, we also have a specialized laboratory data evaluation methods. Usually, class, these are not really that complicated, but it's not for newbies. Okay? So, from the basic methods of organizing, presenting, and analyzing statistical information, there are 3 other techniques that have been developed that have proved to be especially useful in our laboratory. Number 1 is the Lev Jennings Chart, or the LJ charts. These are control charts used to plot quality control values against previously set limits to determine if a procedure is in or out of control. Remember the control charts from the 7 old methods, right? Another specialized laboratory data evaluation method is the Udan Plot. The Udan Plots are used to demonstrate and compare the performance of a laboratory on paired samples with other laboratories using common control lots or a survey material. Udan Plots use the mean and standard deviations from all participants to prepare a chart on which each laboratory's result can be marked to show its performance in relationship to the whole group. Udan plots are divided into 4 areas with a 45-degree line drawn from the XY intercept, separating the graph into 2 halves. Depending on the location of a laboratory's results on the Udan plot, the degree of accuracy, precision, and type of error may be inferred. Udan plots are now frequently being discontinued or replaced with other graphical or numerical displays because of the voluminous amount of computer paper it takes to print out a plot for each analyte and the expense associated with mailing this bulky material. The instrument performance matrix used by Coulter Hematology Reports for its interlaboratory quality assurance program is an example of a technique that has replaced Udan plots. And lastly is the multi-rule analysis. Multi-rule analysis, commonly referred to in the laboratory as the Westgard Rules, that has formalized the application of multi-rule techniques to the medical laboratory. The 6 rules proposed by Westgard and Barry for accepting or rejecting a control run are based on the expected Gaussian distribution of sample values. Implementing a multi-rule program involves management choices about the degree of error that the laboratory finds acceptable when making decisions about the possibility of correctly accepting or rejecting a control run. Each rule is designed to detect or warn of an impending error or malfunction that may either halt the reporting of results until the problem is corrected or signal the need for preventive maintenance. Allow me to discuss to you the different Westgard rules. The first table shows the 1-2s rule. This is usually a warning rule violated when a single control observation is outside the ±2 SD. Some laboratories class consider any quality control value outside its ±2 SD limit to be out of control, and therefore incorrectly decide the patient specimens and QC values to be invalid. An analytical run usually should not be rejected if a single quality control value is outside the ±2 SD QC limit, but it must be within the plus minus 3 SDQC limit. This means, class, that the 1-2S rule is originally designed as a warning rule for manual application of the Westgard Rules. Another Westgard Rule violation is the 10x rule. This happens, class, when 10 consecutive control measurements fall on one side of the mean. In addition, you will sometimes see some modifications of this 10x rule. There are also 8x rule. This means that you have to reject when 8 consecutive control measurements fall on the one side of the mean, either the plus side or the positive side or the negative side of the mean. Okay? It should be consecutive on either side of the mean. Another Westgard rule violation is the 4-1S. This states that the run should be rejected if 4 consecutive control measurements have exceeded the same mean, either plus 1 standard deviation or the same mean minus 1 standard deviation. There is also 1-3S rule violation. This rule states that if a control is greater than plus minus 3 standard deviations from the mean, it should be rejected and rerun. This is either because of a random error or a very large systematic error has occurred. The next rule is the 2-2S rule violation. It states that if 2 consecutive control measurements across runs exceed the same mean minus 2 standard deviations or either exceed the same mean plus 2 SD or within a run, that means if 2 consecutive control values are outside the same 2 SD, the run must be rejected. Lastly is the R4s Rule. This rule applies to controls within a run. So this means that it is on the same run, okay? If 2 controls exceed 4 SD, that is, if one control exceeds plus 2 SD on the other control, or another control, if more than 2 controls are tested, exceeds minus 2 SD, the run should be rejected. In other words, class, there are 2 consecutive control values that exceed either plus minus 2 SD. So if you can see there from the picture, plus 2S is 1 SD, plus 1S is another SD. Then below the mean is there's also 1S and minus 2S. So count that 1, 2, 3, and 4. That is 4SD. So this rule is called the R4S rule violation. Just count the yellow and the green lines, class. Here is the summary of the Westgard Rules. You may take a screenshot of this so that we can proceed to the next discussion. Let's proceed to interpretative strategy. The detection and correction of errors, both technical and administrative, are a major mission of quality management programs. All of the preceding methods are useless if the technologist or the laboratory manager is not aware of the types of problems, errors, or malfunctions that can occur in a process and of the clues that may trigger their recognition and resolution. The old microbiology adage states that we tend to find what we are looking for, applies here as well. Following is a list of some statistical terms and clues that may tip the medical technologist or even the analyst to possible problems. Let's talk about the concept of error. This is related to accept or reject and problem or no problem decisions. An error can be made in either direction, right? A decision can be made to accept a control run. So you may accept a control run incorrectly with the laboratory reporting out incorrect values. So you can give the patient's results incorrectly. Or you may have a legitimate test result that can be rejected, resulting in a loss of time and reagent expense. Control limits must be set with both potentials in mind. The errors class may be classified into two types: a random error, which may occur at any time and place within the testing or service process, and systematic errors, which occur in a consistent direction or pattern. Random errors class are indicative of imprecision in an analytical process, while problems of inaccuracy show up as systematic errors. Identifying the type of error is crucial to determining the extent, nature, and timing of action necessary. For example, a random error may need only to be closely monitored for possible recurrence, while a systematic error may need immediate remedial action. Control charts and the multi-rule analysis may both give clues to the type of error because it shows the violations of what type of rules again? The Westgard Rules. So when we say Westgard Rules 13S and R4s are types of random errors, while 22s, 41s, or 10x or 8x rules that are being violated may indicate that the error is systematic. Manipulation of data. Decisions about what to include in a population or sample are often criticized by those who question the validity of statistical figures. You know those statistics that are given on the TV, like the percentage of those who agree with the current president is like this and like that, and the opposition population against the president is are these values. Usually, class, we have a feeling of indifference or skepticism. That's the term. We have a feeling of skepticism if those values really reflect the entire population of that same country. So, or let's say, for example, out of the 104 million Filipinos, 100 million agrees to the president. How sure are we if truly 100 million of the Filipinos agrees to the president when they only test a certain few of the people, right? So this manipulation of data in statistical figures is really a controversy. Having a set of numbers that do not truly reflect the characteristics of the whole population is referred to as a statistical bias, which may be either circumstantial or intentional. The exclusion of a number that does not appear to belong in a group of data is called an outlier. It's an example of the purposeful manipulation of data. This means that manipulation of data is not an uncommon occurrence also in the laboratory. If a control were run 30 times and all the values were between 19 and 31, except for one which was 54, it is the discretion of the medical technologist to exclude that number. So the exclusion of the outlier from statistical calculations is an example of an intentional bias. This may also be called cleaning up the data, a term particularly attractive to the person doing the refinement. Next is examination of control charts. Clues about data problems are often revealed in the shape of the Gaussian distribution curve. Deviations from the symmetrical bell-shaped appearance of a frequency polygon are called skewed curves. They also serve as a signal that a data do not accurately reflect the parameters of the population. Distribution curves can become skewed in either direction, either to the left or to the right from the mean. So this is because of non-representatively small sample size or by the inclusion of data that are flawed because of sampling or a process like technical or administrative errors. Problems that are not rectified may translate into misleading inferences or incorrect range limits on the Lev Jennings chart. This, as every medical technology knows, or those people who run control runs, may trigger unnecessary out of control flags, causing much frustration and wasted troubleshooting time. There are three problem related patterns that can be detected by studying how data appear when plotted on a control chart. There is trends, dispersions, and shifts. All these three patterns have also been matched with probable causes for their occurrence. The medical technologist or the analyst must also be aware that these patterns may all occur at the same time and be constantly alert to the clues provided by each type of change in data configuration. One of the three problem-related patterns are trends. Trends are marked by a systematic drift in one direction away from the established mean. Trends may be detected by 4-1s or 10x Westgard Rule failures. Trends signal the gradual deterioration of procedure components such as reagents, standards, or instrumentations. Like, for example, the light bulbs, electrical elements, filters, and so on. Next is dispersion. So this occurs when control values are widely scattered in an unusual and unexplained pattern around the control chart, particularly with increasing out of control like exceeding plus minus 2 SD and plus minus 3 SD results and Westgard Rule violations. Usually the Westgard Rule violations are 22s and R4s when you see dispersion. Dispersion class is a sign of loss of precision and may be caused by inconsistency in such areas as a malfunctioning automatic dispenser or variations in technique by the testing personnel. And when we say shifts, these are sudden switch of data points to another area of the control chart away from the previous mean. They are usually associated with change or replacement of some component of the analytical system, such as a new lot of reagents because we need to run another control for this new lot of reagent, repair or installation of an instrument part, or recalibration of the method. By the way, class, shifts are not necessarily bad and may reflect only some action taken to correct a problem previously noted. Here is an explanation of the difference between shifts and trends. When we say shift, QC data results are distributed on one side of the mean for 6 to 7 consecutive days, while For trend, a consistent increase or decrease of QC data points over a period of 6 to 7 days. That would be all for the part 2 of our quality assessment and performance improvement lecture. Please wait for part 3 as we explain the management of quality. Thank you so much for listening to our second session of this topic. I hope you've learned a lot from me today. So keep safe always, class. God bless you all and continue studying. Goodbye.